From today, I will be starting a brand new chapter, and this is the beginning of electromagnetism, and it's a long topic. And as a first chapter, today I'm going to start electrostatics. So we're going to talk about electrostatic, what is static charging, electric charge, electric fields, Coulombs law, stuff like that. And it's a little bit long video. So I'll divide. I'll be making two videos from this lecture slide. So these are the topics for the first part of this video. So charging by friction, as everybody knows, right? If you rub your pen against a floor or your cloth, it can attract bits of paper, something like that. So what causes that? So we'll be talking about charging by friction. It's also called static friction. We'll be talking about electrostatic induction, and forces among the two charges is called Coulombs law. This is just like gravitational law, And the second part of the video will be on electric field, and then I'll be making a separate video on the sample problems as usual. So let me first show you some examples, everyday life examples, and these are all examples of electrostatics or static charging. So and you can clearly see your comb, when you rub your comb against comb your hair, right, and it can sometimes it can attract bits of paper, something like that. So this is how the static charging were discovered. And think about that actually. A charged balloon, first you have to statically charge a balloon, right, by rubbing with the cloth or floor, and then you run a little bit narrow water from the faucet, and it can deflect the water flow. So what causes that? So we'll be talking about that, and these are all examples of these Hughes thunderbolts, is also has to do with the static charging. And this child is here gets pulled, right, gets repelled while she was playing in the slide, and that has to do with the this has to do with the electrostatic charging as well. So here's the static charging example. That's how this electrostatics was discovered actually first. So if you rub a glass rod or any plastic rod, insulating rod, against a floor or any cloth, right, it can attract bits of paper, tiny bits of paper, something like that. So what causes that, right? That's how the electrostatic was discovered. Actually, in fact, this static charging was discovered by ancient Greeks, hundreds of years before, and by rubbing this fossilized resin called amber, and if you rub the amber with flour or any cloth, it can attract bits of paper or other objects like that, and that's how it was discovered. And the Greek word for amber is electron, and that's why all the electricity, electron, electrostatics, the electron name came from Greek. And these are some sample examples, video link. So there are two types of charges actually, and people didn't know in the beginning when it was discovered what causes that. So if you have a charged plastic rod, so charge means you have to first rub it against a floor or cloth, right? Two charged plastic rod, would repel each other. But if you bring that same charged plastic rod with a charged glass rod, they would attract each other. So this simply means, right, it attracts, here it repels. That clearly tells you that there are two types of charges develops actually, right? Static charges develop plastic rod and glass rod. So glass rod and plastic rod have some excess charges, static charges, but they are opposite sign. They must be opposite sign, right? Because this repel, this attracts, right? So two types of charges. And so now back to the main problem. So what causes the static electricity? What causes the charging, right? So, and it has to do with the structure, the atomic structure actually. So matter is made up of atoms, and atoms contain positively charged at the nucleus, because of protons, and surrounded by equal number of negatively charged electrons, so equal number, right? So an object in general is electrically neutral. Okay, so that's important here. So an object, any object in general, right, is electrically neutral. Why? Because it has equal number of positive charge at the center, at the nucleus, right, and equal number of negative electrons surrounding the nucleus in various orbits. From modern theory, we know that. And what happens if when an object is rubbed against another, like fur or cloth, it may lose or gain. It may lose or gain the electrons. That's the main point. So here's the main point. If an object loses electrons, right, it becomes positively charged. Why? Because it is deficit of electron, because it has lost some electrons, right? And whereas opposite, if an object gains the electrons, if an object gains electrons, then it becomes negatively charged, right? So these are the main points to remember. If an object loses electrons, it becomes positively charged. Why? Because it has now less number of electrons. If an object gains electron, however, it becomes negatively charged. Because why? Because it has an excess number of electrons. So that's the main cause of charging, right? Electrostatic charging. That's the main cause of static charging, you would say, static charging. Okay. So, however, you have to understand that protons are tightly bound at the nucleus. Protons in this process, static charging process, protons do not transfer, do not move, right? The only mobile charged particles are electrons. Only loosely bound electrons, right, can actually transfer from one object to other object. Okay, and here are some examples. So we actually always experience this actually in everyday life, especially during the winter time. Actually, we experience this. So first, let's talk about this. Especially in the winter time, because the humidity is very low. Then sometimes if you try to touch the doorknob, you get a mild electric shock, and it's because your body gets charged actually, because of this actually. When you walk along the rug, right, or carpet, your body actually loses some of the electrons to the carpet, and your body gets charged, right? Your body has positive static charge, and when you try to touch the knob, right, your positive charge actually gets discharged to the ground, because the excess charge you develop, gets discharged through the doorknob, which is conducting to the ground, and that's the main physics behind actually this mild electric shock. So total the charge developed. So we already know actually, right, when you rub a rod against a fur or cloth, it develops a static charge. And how much charge will be developed, right, is given by this formula. Is from the conservation of charge, right? So total charge, this is the total charge developed, right, on any object, is N times E, where N is the total number of electrons transferred during this process, and E is the basic charge of electron or proton, which is always constant. This is the basic charge of electron, and then you can find the total charge developed during this static friction, static charging. So for example, in this particular example, since the fur loses six electrons, the total charge on the rod is 6 times this, right? 6 times this. This is the total charge. So since it's a negative charge, so rod gets negative charge. Since fur loses electrons, it develops positive charge. So this positive charge. And C is the coulombs. That's the standard unit of charge. So now let's briefly talk about the conductors and insulators, because you're going to briefly need that. So conductors are materials that allow charges to move freely through them, right? For example, all metals, copper, aluminum, mercury. And what's the reason? Because the reason is because all the metals conductors have at least one free electrons, loosely bound free electrons like this, right? And they can transfer from one atom to other atom easily, actually, within them, right? Through them. So that's why this is called a conductor. Whereas insulators don't have free electrons, and the electrons within the insulator can move freely, and that's why they can't conduct electricity, right? Because there's no free electron in them. So that's distinguished between conductors, and insulators. Okay. So can you charge a metal rod by rubbing it, or by static charging, just like the glass rod or plastic rod with cloth? The answer is no, because since metal rod is a good conductor, so even if you develop some charge, right, by rubbing, right, so that charge quickly actually get discharged, right? The positive charge, say metal rod, right, and that will be quickly discharged through your body, because you're holding this rod, metal rod, with your hand, and you're standing on the ground. Your body is providing some ground path, a path to the ground, and then whatever charge develop, excess charge develop, will be very quickly drops to zero, like, because you're grounding it, right? You're discharging everything to the ground, and that's why usually metal rod cannot be charged with static friction. And now next important part to understand is electrostatic induction. Okay, so what is induction? So induction is this. This is the definition. It's the redistribution of the electrical charges in an object caused by the influence of the nearby charges. So, for example, here's this JF animation. Let's see, it explains clearly, right? So this is a material, say, right, metal, say. It has equal number of positive and negative charges distributed equivalently, right, symmetrically, so that then it's neutral. Now, what happens if you bring a charged glass rod? Say this is a charged glass rod. Glass rod has a positive charge when it is charged. Now, this will happen. So first, let's bring the positive charge. So when you bring a positive glass rod, it will attract actually all the electrons towards it. So it polarizes, right? It polarizes here, right? And when you bring a charged plastic rod, which is negative, it will repel all the electrons to the other side. Actually, it will redistribute, right? It will polarize the charges in the given object, and that's the reason. That's the reason actually a charged glass rod or charged charged plastic rod can attract a bits of paper or any neutral object, and it's because of this. Look at this. When you bring a charged glass rod near a neutral object, it will polarize the charges. So negative electrons will get attracted towards the positive rod, and positive charges gets, right. And because of that, it has now this neutral object becomes a dipole, and because of that, it attracts, because this negative charge here is near to the glass rod, positive charge, compared to the positive charges. And then what's the net result? The net result is you have attraction, right? Net result is this, and that's why a charged rod, any charged rod, glass rod or a plastic rod, can attract a neutral object. That's the main, and it's because of induction. You have to say induction. And you can just check this diagram, how you can charge any object without touching it. Actually, just see this video one, just see this actual diagram one by one, you will understand. So here's conventionally, the static charge is measured using electroscope, and it's called gold leaf electroscope. Why? Because it has a very thin pair of gold leaf, hanging here, attached to this. And then when you touch it by a charged rod, right? Let's say a charged glass rod, it will transfer some of the charge, since both leaves get the same type of charge, they get repelled when this sensor is touched by a charged object. And there are two things actually. You can charge it by induction, and you can charge by actually touching, and you have to understand why it happens. So I'm just briefly actually all the whole chemistry actually, which is based on the attraction or repulsion between two charged molecules, right, atoms, is based on this electrostatic bond, electrostatic attraction or repulsion, right? So for example, hydrogen bond, which happens between these four atoms, is the cause of the binding between this DNA molecule actually, because guanine, cytosine, thymine, adenosine, they form a weak hydrogen bonding, and that's because of we have life, Okay, now next important part is to do any numerical problem. First, you have to understand Coulombs law. So Coulombs law is just like Newton's law of gravitational. Coulombs law gives the force of attraction or repulsion between any two charges. Now we know that right? There will be a force of attraction or force of repulsion between two charged particles. Now, but quantitatively, how much, right? So then Coulomb's law actually can actually calculate the force of attraction or repulsion between two charged particles. It can calculate the magnitude. So it simply says this: the force acts along the line connecting this. Say you have a two positive charge, you have force of repulsion, right? If you have positive charge, negative charge, you have force of attraction, right? You have both. It could be repulsion force, it could be attractive force. And it says this actually, the force of attraction is inversely proportional to the square of the distance between them and directly proportional to the magnitude of the product of the charges. That's what the Coulomb's law. And this equation is basically the Coulomb's law. It's K Q1 Q2 magnitude divided by square of the distance between two charged particles, right? And this is called Coulomb's law. And here K is called electrostatic constant or Coulomb constant. It's always a constant number. It's a big number. It's about 9 10 to the power 9. This is the unit. That's the big number actually for the Coulomb constant. And here's some again explanation. It is just like this Coulomb's law, right? Is very similar to gravitational law. The only difference is gravitational force is very small, like almost negligible compared to the Coulomb, compared to the electrostatic force, because this value of K is much bigger than value of G if you check the values, right? These values. Okay, again, if you bring these two objects close to each other, the force of attraction will be much bigger, right? Because of this inverse square law. And here's the again formulas. So you can write it down like this or like this. Remember, you just need the magnitude. You just need this Q1, Q2 are the charges, right? Charges on two charges, and you just need the magnitude. And the unit of charge is coulombs. Okay, unit of charge is coulombs. And here are some practical units. 1 microcoulomb means 1 millionth of a coulomb, 10 to the power -6 microcoulomb. Right? 1 nanocoulomb means 10 to the power -9 coulombs. It's a billionth of a coulomb. Picocoulomb is even smaller, right? 10 to the power -12 coulombs. These are the practical units of charge, because 1 coulomb is a big charge. So practically you will be dealing with actually microcoulomb or nanocoulombs. And to solve this now, this Coulomb's law problems or electric field problem from now on, you need to review the vector addition and vector subtraction, vector algebra basically. So just let me give you a very brief actual review of the vector. So if you have three forces like F1, F2, F3 acting at a point like this, right, and they make different angles with the x direction, or it could be y direction, then the question is, what is the net force acting at that point? So then you need the vector. So the first thing is you have to resolve, right? You have to decompose each of these vector using trigonometry into two components. This is the y component, sin theta, cos theta is the x component. Do this for second force, do this for all the forces, and summarize this. Put all the x component on this table, this side, put all the y components on this side, and then sum them up. All this, right? Sum them up. Each of these will have a number. And how do you find the magnitude? This should be the magnitude actually. The magnitude of the force is then the sum of the x square plus sum of the y square, and what's the direction of the resultant force is given by the inverse tan y force, sum of the y force, sum of the x force, and also mention the coordinate. So this is a very brief review of the vector addition. So here's an example again vector. If this is the top view of the box on a frictionless table. So if this box is being pulled by two forces with the help of rope, right? Where does this box move? How will the box respond? In which direction will the box move? And well, the box will move in the direction of the net force, right? That's why we need the vector addition. Just like that, you're going to need the exactly same idea for solving electrostatic problems. And this is again a brief review. Okay, so make sure you review this. So first you need to figure out the sum of the x forces, sum of the y forces, and then net is given by this, and the direction is given by that. Right. So some important sign conventions. So if uh, so this force is attractive, right? And if you bring these two charges close to each other, the force will increase. The magnitude of the force will increase. Similarly, the repulsive. This is the repulsive force. And then I'm going to show you a separate video on some sample problems.